All right, everyone, welcome to the DDPS seminar. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me introduce our speaker today. It is an honor to host Misha Khodak, who is a PhD student in computer science at Carnegie Mellon University, advised by Nina Balkan and Amit Talwalkar. His research focuses on foundations and applications of machine learning, in particular, the theoretical and practical understanding of meta learning and automation. He's a recipient of the Facebook PhD Fellowship and has spent time as an intern at Microsoft Research, New England, and also the Lawrence Livermore National Lab and the Princeton Plasma Physics Lab. Previously, he received the AB in mathematics and the MSc in computer science from Princeton University. Today, Misha will talk about towards automatic architecture design for emerging machine learning tasks, which is very interesting topic. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Misha by asking one random question as usual. Today's random question is, what is your favorite things to do other than research?
I like to ski and I'm learning how to garden very slowly.
Oh, garden. Okay. Are you good at skiing?
I'm decent at skiing, I think.
Yeah, probably you're better than me. All right, the stage is yours, Misha.
Sounds good. Yeah, thank you so much for inviting me. My name is Misha Khodak and at CMU. And today I hope to give you some description of some work we've been doing to design new operations for machine learning tasks, going beyond the classic tasks that we all know, like vision and text that machine learning is good at, towards emerging machine learning applications. So let's get started. So the past decade in machine learning, as many of you probably know, has seen a lot of advances in many different areas. So it started at the beginning of the decade with this developments from University of Toronto and Google in vision, so object detection with applications, for example, to self-driving and text applications. So machine translation was a really big deal. And then later in the decade, there was a lot of progress from especially DeepMind and OpenAI. So these large, well-funded startups on things like game playing, protein folding, even more advanced text models. And so this has really been kind of a large amount of progress in a very short amount of time, spurred by deep learning models, neural networks, and so on in machine learning. So they've achieved these impressive results in a few specific domains, such as vision, so image classification, segmentation, and text, such as language prediction, translation, and some other tasks where you have a good control over the environment, for example, game playing. What the focus of this talk is really that we believe that this is really scratching only the tip of the iceberg for what machine learning can be applied to. So at the top, you can see we have things like transportation. So image detection can be used for autonomous vehicles. Audio has had a lot of progress. Text has had a lot of progress. But at the bottom, there's many other things that deep learning has. Maybe there's been some applications, but it is not an established field where people are constantly developing new models, and there's lots of funding and lots of discoveries for these areas, such as PDE solvers, medical applications, ad tech applications, all the way down. We think there's a lot of these applications that are so far underexplored that deep learning can be very easily applied to, or should be very easily applied to, but is not yet. And the reason it's applying deep learning to these new applications is trickier is because of the type of neural networks being used for them are not actually well tuned for them. So we have these neural networks that are very effective for vision, for text. We've developed very advanced and sophisticated methods that encode the right biases for these deep nets. On the other hand, when we have data such as experimental data from the natural sciences, simulation data, data based on graphs like social networks or protein graphs, or biological sequences, we don't really know what neural network we want to use for them. And the goal of this talk is to push us towards automating how to discover neural networks for applying deep learning to these emerging tasks. And so the question we're going to ask is, can we automate this tuning of neural networks and to enable the straightforward application of deep learning to many new tasks that people haven't been applying them before? So first, let's discuss what a neural architecture is. And maybe many of you know what this is, but we should go over it anyway, just to make sure we're all on the same page. So a standard picture we have of a neural network is you have some input, such as an image, and you pass it through a lot of matrix multiplications of some kind and nonlinear operations. For example, logistic functions, sigmoids, that sort of thing. You pass it through several layers. That's why it's called deep. And the goal is to learn what numbers to put in these weight matrices so as to output the right classifier at the end. So the 0-1 encoding of the word frog, say if the input is a frog. And to train or to learn the numbers in these weights, what we usually do is we specify some objective that's large if it's the wrong answer and small if it's the right answer. And we apply gradient descent to these weights. And magically, nobody knows why, it seems to work well both in terms of training and that we get global optima in training, and also we do fairly well on test performance, so out of sample performance on samples we haven't seen. And this requires collecting all of data, but it seems to work pretty well for some tasks, especially computer vision. Now, this is a very simple neural network on the left. On the right, we have a much more complicated neural network, that we've actually been designing. So this is kind of what we started with very simple operations. What we're actually designing in a neural network is this general computational graph where you have an input. It's going to be passed through multiple edges. On each edge is some operation. So for example, a linear multiply followed by nonlinearity, it could be an operation. And they're parameterized by a model weights W, and then the inputs to each edge will be passed these operations. And then as you go forward through this computational graph, these edges can combine their inputs at each node. So for example, node 4 will combine the inputs of this edge and this edge through concatenation or addition or something like that. And you pass it forward through this graph, and eventually you come to your output, which you hope again to be something that's correct for the input. And so we have been designing architectures, neural networks, or the deep learning community has been designing these for a very long time. And so this human-driven architecture search, as we call it, has generally proceeded in two different directions. One direction is discovering which operation we want to use. So in the first slide, we had like a linear operation, but of course, what really powers computer vision, for example, these days are these convolution operations where instead of just multiplying the entire input by a matrix, we apply this convolutional filter which slides along the input and only allows local interactions between pixels to propagate to the immediate next layer. And there's been a lot of other designs for what we actually put on the edges of this graph. Most recently, transformers have transformed the field and allowed a lot of progress in things like protein folding and so on. The other direction that people proceed in designing architectures is in network topology. So which of these edges, how do we connect these edges? Like, is edge 1, 3 on or off? Should we concatenate or add, and so on? Probably the most famous of these network topology discoveries in human-driven architecture search is the ResNet, in which we pass an input X into this node, and then there's one edge that applies some convolutions to that node, and there's another edge that just applies the identity operation, and then there's summed at the end. So basically, which operation to use and how to connect them is kind of a topology search question, and discovering operations themselves, so discovering things like convolutions, discovering transformers, is more of an operation search question. So these are the main directions of progress that humans have been developing architectures for the past decade and even earlier. Convolutional neural networks were discovered in the 90s. As many of you have probably seen this image of the improvement of ImageNet on ImageNet, so this big image classification benchmark over the past 10 years. And what I actually want to show in this plot is how important these discoveries of new neural architectures have been to drive this progress in machine learning, for example, on this benchmark. And not only that, but also how complicated these architectures have been. So on the bottom, you see the best architecture from each year up through 2015, and you can see it keeps changing. And if we zoom in on one of these architectures, this is called GoogleNet, we can see it's very complex, expert-driven architecture design here. So we have a lot of weird choices that these architecture designers made. So for example, we have the structure where we repeat blocks of the graph as we propagate the input from the left to the right. We're going to somehow connect internally, we're going to connect these blocks somehow. So we have edges from certain nodes, but not from others. So for example, there's no node between this one and the input here. We have a lot of different operations we might want to use. So in different places, we're going to use a convolution with a kernel of size 3 by 3. In other areas, we're going to use a convolution with a kernel of size 5 by 5. We might use different types of pooling where we gather local pixels together by taking a max or an average of them. And of course, we also chose to use convolutions anyway. This was also an architecture decision. And the question becomes, say, if we're not applying to a vision task, why are we using convolutions anyway? So these are the sorts of very complicated decisions that in architecture search we have to consider. And so the goal of neural architecture search, as opposed to human architecture search, is to automate away this design of architectures so that non-experts can apply it to their task, or to help experts get even better performance, like eke out the last few accuracy percentage points from their tasks. So you want to help practitioners in advanced areas of ML where machine learning already does well, such as vision, language, and so on. And you also want to accelerate progress in new areas, which is our goal today. And I think there has been a lot of progress in neural architecture search over the past 3 years or so. We've discovered that this repeated block structure just always seems to work. So this is often not something we search. We have lots of architecture search algorithms. We've worked on them. Many other people have worked on them to select which topology to use within each block. We have a lot of algorithms for picking from a small set of operations which operations to use within each block. We don't really know why we're using convolutions for a lot of these other tests, but for images, they seem to work. And these days, if you have a new application, the first thing many people do is they're going to apply, say, a ResNet or a VGG or something like that, a convolutional neural network or a CNN, to their problem and hope for the best, at least initially. And so the focus of it, unfortunately, the focus of this existing neural architecture research has really been on this first bullet point, which is to help practitioners in areas of ML that already work. So these architecture search methods glue together existing primitives, so existing operations like convolutions, and those we know already work well on these heavily studied tasks like vision. And the question really becomes, like, why are we studying architecture so heavily, or architecture search so heavily, if companies like Google and so on already have many engineers that can be applied to these tasks? You know, why are we working on this field when we have this whole other area of research that we might want to work on to accelerate progress in new areas? So specifically, we want to design a search space in this work that can serve as an initial automated solution to machine learning problems on diverse domains beyond vision, text, audio, and so on. Before I go forward, are there any questions about the motivation of the work? Great, so let's start first with defining what the neural architecture search problem actually is. So remember, we have this computational graph, and our goal is to pick an operation for each edge in this computational graph to maximize some objectives such as accuracy, latency, efficiency, memory, and so on. And so here's our graph, and there's a computer that's running this architecture search algorithm. And usually what people do, if you have a standard discrete neural architecture search space, is we're going to pick which operation should we use on each of these edges. So are you going to use a convolution? Are we going to use an average pooling, or so on? And this also more or less covers the network connection question, because one of these operations could be the none operation. So we don't pass any input forward, and then this edge is just not connected. So if we have a small set of operations, we're going to define it using our search space. And for example, this very popular search space called darts has 8 different operations, such as the identity, so just pass the input forward, the zero operation, as I was describing, pass nothing forward, and some convolutions of various kinds, and some pooling of various kinds. These specific operations aren't that important, but this is kind of the standard approach in neural architecture search. Define a very small set of operations and figure out where in your neural network to put them. Which edge do we put which operation, and hope that this is what we need for our task. And we know convolutions, so all these operations are sort of convolutional, as we'll see. We know that these operations work well for vision tasks. The question is, does a search space consisting of just these operations, would this work well for other data domains? So for example, other data we might consider would be sequence modeling. So if you, for example, want to figure out what the next word is in your sentence that starts with neural architecture, and you might want to have search here, this is a sequence modeling problem that can be modeled as a multi-dimensional array input with one sequential dimension and one kind of vocabulary dimension. And here it turns out convolutions work okay, but need to have some special designs to actually work well, like large dilations. And other operations like transformers work even better. There are other operations, and this will be the focus of our empirical evaluation, at least in this talk, is in, for example, solving partial differential equations. If you have, say, an input at time 0, can you use classical solver data to figure out what the fluid state should be at time 50? And here it turns out convolutions work poorly, although they are closely related to some state-of-the-art operations, such as Fourier neural operator, which I'll get into later. And then there are many other problems we might want to use, such as prediction on graphs, where regular graph convolutions regular convolutions don't even make sense, but there are graph convolutions that do work well. So we have these many other applications, and many I'm not listing, that we don't know that we can just apply convolutions and expect good performance, and in some cases we actually get bad performance. On the other hand, a lot of these operations actually, even when we use new operations, such as the transformers or this state-of-the-art PD operation, or this graph convolution, we are using fairly basic topologies. So we're using this residual network topology here, or just a basic like feed forward, like the first neural network plot I showed you is being used here. And so the question of how we can handle these domains, we think has a pretty simple solution, but some other possible solutions are we can just use this search space, this very small operation search space anyway. We believe this will give you a large gap in performance. This has been seen empirically. And it's not going to discover truly novel architectures. It's just going to glue together convolutions, pooling layers, and so on. We can also add new operations one by one as we discover them. Unfortunately, a lot of discrete NOS methods don't scale well with the number of operations, and we might not know the right operation to use. So we would have to, employ human effort and not automation to discover a new operation for a specific task. And so our argument here is that we need a more general search space focused on operations and not on the actual topology of the network. So we're going to construct a new, more general search space in this talk. And the way we're going to do this is we're going to start with the darts operations. So remember, it's going to contain the identity operation, the zero operation, multiple kinds of convolutions, and pooling layers. And we're going to observe that 7 out of 8 of them are linear. So if you give them some weights, and you give them an input, then the action of the operation can be expressed as a matrix multiplied times this input. So that's the first thing we can observe. And then we can also observe that since they're all basically convolutions, then you can diagonalize this matrix AW by the Fourier transform, or the DFT. So they have this diagonal form where you apply the Fourier DFT to the input, you multiply it by the Fourier transform of your weights, padded, which is this underline is just a padding that doesn't matter too much, and then you take the inverse Fourier transform of the product, and so this can describe any of these operations with some modifications, and what this allows us to do is to replace these discrete Fourier transforms by a more general family of efficient matrices. So this is how we're going to construct a new search space based on diagonalization rather than just combining operations using a 0-1 approach. So before actually discussing what this more general family of efficient matrices is, I'm going to keep going in how we're going to use them. So, we're going to replace each of these DFTs, so discrete Fourier transform matrices, by some other matrix, K, L, and M. And we're going to call these the architecture parameters of our search space. So they define what specifically K, L, and M is going to define the search space we're going to use, how we're going to encode new operations in the search space. And we call this search space XD for expressive diagonalization because you get, basically by allowing your matrices to vary beyond the discrete Fourier transform, you get a more expressive diagonalization than if you just use the convolution approach. So which family of efficient matrices are we going to use? The family we want was introduced by our collaborators in 2020, and they're called Kaleidoscope matrices, or K matrices. And this is a really neat family of matrices. It's basically you take the Fourier, the FFT algorithm structure. So as many of you probably know, the FFT operates by applying a successive number of small matrices to the input, where each of the entries in these small matrices is some roots of unity. And you apply this successively, and since they're nicely structured, you can get a very efficient algorithm to apply your DFT to your input. And so what this paper proposes is to replace all the entries or all these roots of unities in the discrete Fourier transform to allow them to take on any complex number. And the reason this is interesting is that by doing this, you can provably express any efficient matrix vector operation. So any matrix vector operation that can be applied to an input in linear time. So what this is going to include is sparse operations, low rank operations, permutations, discrete Fourier transforms, discrete cosine transforms, wavelet transforms. So many different operations that we're going to see are very useful in architecture search. So going back to our applications, we're going to substitute these K matrices in for this discrete Fourier transform and use them to define our architecture space. So K, L, and M, which kind of encodes what operations we're using, will basically define how big our architecture search space is. And the reason this is nice beyond the properties of the K matrices I discussed is that all of this preserves the efficiency and short description length of convolutions. So all of this, because K, L, and M are still have this fast Fourier-like structure, they still maintain the efficient matrix vector multiplication quality. So we're not just using arbitrary matrices that would be too complex. But on the other hand, it allows us to express many different operations of interest. And specifically, it allows us to express all but one of the operations in the Dart search space. So that search space I discussed before, all of them except max pooling, so average pooling, convolutions, dilations of various kinds. They're all included in this search space, which I'm representing by this blue blob. It also is going to include all convolutions in the popular Python neural networks package called PyTorch, which has many dilated convolutions. It has transpose convolutions, and so on. It can express all of those convolutions. So it can search over, like when searching this operation search space, it can search over all these convolutions. A very neat result is that we can actually express graph convolutions for fixed graphs. And the reason we can do this is because graph convolutions basically depend on multiplying the input by the adjacency matrix of the graph, roughly speaking. And since the adjacency matrix is sparse, it can be represented by K matrices. And so it is contained in our search space once you work out the math. And finally, yes.
What about the fully connected layers and activations?
So fully connected layers is kind of a tricky question. Some people might say that fully connected layers are equivalent to a convolution with filter size 1, but that's not necessarily the case. The issue with fully connected layers is that they're a bit too expressive if you apply them to the full image. So we can't necessarily express those unless you allow your parameter space to be really large. Your other question was about activations. Activations are a nonlinear operation, and so we can't actually express them. One of the key things we identified with all these darts operations is that 7 out of 8 of them were linear. So they had this form where once you gave them parameters, they could express AW. They could be expressed as a linear matrix multiplied times X for some A, right? But nonlinear activation functions won't have that property. So that's why we can't, for example, have max pooling and also activations. But we can still search over them using some other algorithm. It's just, it won't be covered by this search space.
Okay.
Thanks for the question. Right, and so the last thing I think that's very neat also is that it expresses the Fourier neural operator. And I'll get into exactly how it expresses that later. And this is the state of the art, at least before us, for these neural PD solvers that people have been developing, at least on the benchmarks that they test. Okay, so now that we have this search space of XD operations, we're going to briefly discuss how we can actually use them. And to do this, we're going to modify the standard pipeline for how people might use other deep neural networks in practice. So the standard pipeline is you obtain your data, you choose some convolutional network topologies such as LUNet, ResNet, VGG. There's many networks that people have come up with. And then you're going to apply this neural network to, and by training model weights for it, by using stochastic gradient descent or some other gradient-based optimization algorithm, such as ADAM, on some loss function, depending on how well this network fits your data. And then what you're going to do is it's not going to work the first time. So you're going to evaluate how well it did on some validation data, say, and tune as needed. So tune your optimizer, maybe choose a different topology, so on. The way we're going to apply XD operations is quite simple once we've just basically a simple insertion into the standard pipeline. What we're going to do is replace all convolutions in this convolutional mirror network by an XD operation initialized as convolutions. We're going to call this also warm started as convolutions. And the way we specifically do this, as if you remember the K matrices that we use to parameterize our architecture search space, we're going to initialize them as the DFTs or inverse DFTs as needed to kind of make sure that the network starts as a convolution, because it seems convolutions are a good starting point at least. And then we're going to allow them to vary, these architecture parameters to vary together with the model weights by also training them using some algorithm, such as stochastic gradient descent or ADAM. And again, we will tune this also as needed, but it's just basically an extra, a little amount of tuning for the architecture optimizer. So before I get into some empirical results that we have, are there any more questions on the setup and on the design of our architecture space?
Sorry, on the previous slide, I'm not clear. Are you doing bi-level optimization as in differentiable architectures, or is?
It's a great question. So in this work, we don't do bi-level optimization. In this work, we're actually just going to do simultaneous training of the model weights and the architecture parameters. This does indeed go against some, or maybe most, architecture search algorithms to do this bi-level optimization step. And there's no real reason why you can't apply it to in our case, but we found that simultaneous optimization, so single level, works well enough and is simpler. So we used single level in this case. That's a great question.
Okay, thank you.
So I have one question. I think I'm following all this, but just to make sure, there are no integer variables. Everything's continuous.
Yes, this is an excellent question. Indeed, there is no integer variables or no like binary variables and so on. And this indeed is kind of a difference from standard architecture search algorithms or search spaces, right? Where it's really a question of, do I use a 3x3 convolution or a 5x5 convolution or an average pooling? These are all discrete questions that you can encode as indeed an integer or kind of like a binary string. And so, yeah, there's no discreteness here. So we train these architecture parameters, and after training, we don't do anything with them. We don't have to discretize or anything. We can just apply gradient descent and be happy.
Yeah, that's awesome. Thank you.
Yeah, great questions. Okay, great. So I'll keep going then to discuss some applications which we're pretty excited about. I'm going to really focus on the applications that I think are very relevant to Livermore and I think are the most exciting kind of discoveries in our work. But before going into that, we do have a variety of different tasks we've evaluated on. So remember, our goal was to see how well neural networks do on a diverse set of tasks. So kind of to present this work, we need to evaluate on a diverse set of tasks. So for example, as a baseline, we started by seeing, regular CNNs do well on regular image classification. The question is, or what we try is permuted image classification, where we apply a permutation to the rows and columns of an image. So for example, this image of a horse, if you apply some permutation to it, you'll get what looks like nonsense on the right. But in principle, if you unpermute this, then you should be able to do just as well with a CNN as long as you have a permutation in front of it, right? So we apply it to that, we do much better than a CNN. And partially the reason is because permutations followed by convolutions are also an operation in our search space, which is great. Unfortunately, we don't do quite as well as exactly unpermuting and then applying a CNN. but that's, of course, I think quite a difficult problem. And then we go on to less toyish tasks. So for example, predicting distance prediction in protein folding, which is a two-dimensional problem where you extract some features from your protein strings and you try to predict the correct distances between them. And this is part of the kind of protein folding pipeline that's been popularized by things like AlphaFold from DeepMind that you may have heard. They use a transformer model here. It's much more advanced, but we're just doing a baby evaluation and comparing to CNNs. And we also outperform CNNs at least here. And also we look at next note prediction in sheet music. So kind of an alternative to language modeling, you can predict notes in like what is the next note in a chorale or a fugue. And here we also outperform regular convolutional neural networks with, even if the neural networks have this custom designed dilation pattern. But the focus, I think, of this talk will be on neural PDE solving. So I'll get into that now. So neural PDE solvers, maybe many of you have seen some of this work, but the setup is basically that you want to sample problems, partial differential equation solving problems from some distribution over the initial conditions of, say, a fluid state. And for each problem, we're going to generate a quote-unquote ground truth solution. It might have error as classical solvers do, but we're going to generate this, what we'll call a ground truth solution using some standard solver such as Crank-Nicholson, or we can go more advanced, but this is what the machine learning community has used. And we're going to train a neural network to learn a function from these initial conditions to a later state. So at time equals 0, we have this initial condition of the fluid state. We'll run Crank-Nicholson to get the solution at time equals 50. And this is going to be our training data. Our goal is to train a neural network that predicts from some distribution over initial conditions like this, what the final state of the fluid will be at time 50. And the targeted application here is to directly use this. So I think if you have a kind of a repeated need to solve partial differential equations, starting from some distribution over similar initial states and similar boundary conditions and so on, then this might be useful because this will only be one forward pass through a neural network rather than running an iterative solver for many time steps. Another big application of this is inverse problems. So here, if you have a final state and you have some distribution that you want to solve over initial states, can you learn solutions such that you can basically sample from your initial distribution and basically speed up your Markov chain Monte Carlo algorithm for your inverse problem to figure out the initial state faster. And then, of course, there's the idea of transferring to new problem domains. Say you have, say you can train a very coarse-grained solver, neural network solver. Can you use that to improve a classical solver and so on? And so the operations that people have been using for training these neural PDE solvers really started with the standard approach of, can we apply convolution to this problem? So this is going to be the baseline we're going to use. People apply a CNN to these inputs. They're nice 2D, 1D, 3D inputs, so we can apply our standard convolutions to them. Unfortunately, convolutions don't work quite well here, at least in the settings we've looked at, and many other people have looked at. The performance decreases as the resolution increases. And so the issue is, as you want to increase the resolution of the grid you're evaluating on, the performance is going to get worse. And in general, the performance is also just not good. The relative error is high, as we'll see. Now, this year at a machine learning conference, there was introduced this Fourier neural operator, or FNO, from a group at Caltech. And it resulted in much stronger performance that was 3 orders of magnitude faster than traditional solvers. So this was not an improvement over convolutions, but the forward pass through this network based on this Fourier neural operator was much faster than running a traditional solver on the same problem. And you got consistent performance also across resolutions, which was a big plus. And now what we're going to do is compare XD operations to these two older operations. So the great thing about XD operations, and we didn't design it this way, but we've discovered that XD operations contain a lot of existing things. They contain both convolutions and FNOs. We'll see FNOs, how they contain FNOs in a bit. They are slower, but we still believe they're fast enough to be useful. So they're basically maybe 2 to 2.5 orders of magnitude faster than traditional solvers, rather than 3 orders of magnitude. And we'll discuss some ways that we're looking at to improve their efficiency. So first we'll look at what this Fourier neural operator is. And basically what it is you take your convolution and you get rid of this Fourier transform that you apply to your filter weights. So it's basically the identity operation. And then you basically apply it in the same way you might apply a convolution. And the great thing about this, in our case at least, is that this of course is also an XD operation, right? Because we used to have a Fourier transform here to initialize our K, L, and M. Now we know that an identity operation is a very efficient operation. It is contained in the set of K matrices we're using to encode these. So it is of course also an XD operation. And these Fourier neural operators on, say, an inverse problem requiring 30,000 solves, they can determine the initial vorticity of a Navier-Stokes system in 2.5 minutes, at least as advertised, although this kind of hides the 12 hours it takes to generate the training data using Frank-Nicolson and to train the network. But it's still faster than your standard solver, which takes 18 hours. Now this is FNO, this is not us. But this is kind of the motivation of this work and kind of the baselines that we're going to be comparing against. Are there any questions so far? Okay, so the experiments we're going to consider, taken directly from previous work, is the Berger's equations on the domain from 0 to 1 with random initial conditions, a Darcy flow on a 2D domain, also with random initial conditions, and 2D Navier-Stokes on the 0 to 1 domain, or 2D domain, but also with the time domain, and with some random initial vorticity. And the discretization is going to just be a square grid in time, and we're going to measure performance as the average of squared losses over grid vertices normalized to the, so basically the relative error. And we're going to borrow all backbone networks and settings from this previous FNO paper where possible to ensure fair comparison. Okay, so on the 1D and 2D problems without the time component, so the kind of simpler problems to study, this is how CNN does. So on the x-axis, you have the resolution, so starting at around 100 cells and going up to about 10,000 cells in the 1D case, and from around 100 to 400 cells in the 2D case. You can see that as you increase the resolution, the performance of the CNN backbone gets worse in terms of L2 relative error. So it starts off not great, and it gets worse as you increase the resolution. On the other hand, this XD approach, so we basically insert XD into, so initialize with the same network, the same convolutional neural network, but allow both the model weights and the DFTs, so the K matrices initialized as DFTs, to vary. And if we train them together, then it turns out that we can get good and consistent performance across resolutions. So you'll see that we have much better performance, and it's much flatter, especially in the 2D case on Darcy flow, but also in Berger's equation. We basically get good performance across all resolutions using this approach. And it turns out it's even better than this custom design for a neural operator approach, which does do much better than CNN, but remember is custom design. All we had to train our approach was our XD approach and knowledge of convolutions, whereas the FNO was custom designed. So even though we knew that that FNO was contained in the XD space, we didn't use it. We didn't use that fact to actually get this good result. And it turns out that if you initialize XD with FNOs, it actually does slightly worse than initializing them with convolutions, which is a somewhat surprising result to us, considering how much better FNOs do here. And then our second or our last set of evaluations for the PDE problem, we also looked at Navier-Stokes, and here we got a very similar story. But here we're tracking across viscosities rather than resolutions, again in terms of L2 relative error on the y-axis. And you'll see that we again do much better than CNNs using XD operations, despite initializing our architecture search with a convolution. And it again does slightly better than the FNO in this study. So to recap, the reason we might want to use our XD operations the reason why we think this is an exciting line of work in general for many applications and not just PD solvers, is that you can transform any convolutional neural network backbone, so a ResNet, a VGG, and so on, into a search space over operations, and you can find something better than convolutions for any problem you might think of. And so in this work, I've really focused only on the partial differential equations operation, but we've looked at a lot of different applications where this has actually worked well. So for example, we've found it works well on permuted image classification, or image classification where instead of permuting, we just flatten the image and pretend it's a 2D or a 1D problem. So these are kind of toy problems, but our approach works well here. As we discussed, it works quite well on neural PD solving. It works well on this module for distance prediction for protein folding, which is an emerging application that people are applying many models to. There's a lot of focus on this, but I think the fact that it works, that just starting from CNN and our approach already improves upon that, is a positive sign. And it works. We've also seen improvement both on kind of classical sequence modeling tests, so language modeling, like text prediction, predicting the next word. We saw some improvement over convolutions there, but also in less studied tasks like music modeling, or some also results on financial time series. Of course, not everything can work well on everything. So to be completely transparent, we've also not done a lot better than the baseline on kind of your more standard tasks like image classification. So convolutions seem to already work great for image classification, and we so far haven't seen our operations improve upon image classification yet. And similarly for audio classification, it seems that convolutions do quite well, and we don't see much improvement using these XD operations. I think, broadly speaking, I think these results where we do much better on some applications and not others is indicative of the fact that, you know, these existing applications are really located in this tip of the iceberg setting where we've studied them for a long time, and we're not going to possibly see much improvement using or see very strong improvement using something like a more general search base for operation. On the other hand, I think a lot of these applications do come in the more emerging applications in machine learning or off machine learning. And we hope to see a lot more progress using something like this or work that builds on it in the future. Now, I'd also like to get into what XD is not. And it's not a replacement for classical topology search, neural architecture search algorithms. So for example, the Dart space, I think Deep Hyper from Argonne, and many other approaches that kind of decide which operations to use where, and so on, decide connectivity in the neural network, and so on. What we believe is that these remain important, and that XD is solving a somewhat different problem of discovering new operations and not necessarily connecting existing ones. And we haven't done this yet, but I think the right approach here is to use them in conjunction with these classical approaches to neural architecture search, where for example, we might find a good convolutional neural network first and then apply XD operations. And the reason we think this is a good idea is because so far, at least in our evaluations of things like darts and not Deep Hyper, but things like Auto Deep Lab on, for example, PDs, shows that they alone, using them alone is not sufficient to get good performance. So for example, is Auto Deep Lab, which is a classic neural architecture search approach, actually does get consistent performance across resolutions, but consistently bad performance compared to, say, the FNO or the XD. So we believe using them in tandem might be a fruitful direction. It's also not a direct way to improve efficiency of your network. Applying XD to a CNN, so there is a large cost to replacing your DFTs by XD operations or by K matrices. It is 5 times slower to train, for example, on the PDE task. On the protein task, it's 2 times slower. And similarly for inference, it's currently slower. And these are things we have to work on in order to get this to actually perform well and be useful on some of these tasks, especially if computation is critical for usefulness, such as in the PDE task. And there are also large memory costs currently associated with this. So yeah, this is definitely kind of ongoing work that we're working on. And specifically to get into this, the inefficiency in XD operations is actually pretty hard to nail down. But there's dependence on new software for K matrices. You know, we're competing with this paper with FFTs, which is a classic algorithm with lots of work over many years, decades. And we're competing, we're replacing this by something that was introduced a couple of years ago, maybe 1 year ago. And we're basically still working on how to actually make this fast. And there's other reasons we can't take advantage of, say, the Hermitian symmetry of DFT. And the kernel filters, we have to pad them to the input size before multiplying them. And this, of course, all adds to the complexity. But ongoing efforts is to actually develop this better software or to develop alternative structured matrices that are more GPU friendly. So all of this is trained on GPUs. How can we make structured matrices that are as expressive or similarly expressive to these K matrices, but actually make them run efficiently? And also developing approximations or truncations that can speed things up while not losing too much in accuracy. We're also working on benchmarking. So as we proceeded with this problem, it turned out that evaluating neural architecture search on many of these tasks was more non-trivial than we expected. It's difficult to define what a diverse task is. How many do you need to evaluate on? How do you actually compare different methods if you have a lot of tasks to evaluate on? And how do you consider computational trade-offs? So this is something we're working on with this benchmark for neural architecture search called Massbench 360, which can be found at this website. Currently, we have 10 tasks, which are understudied but feasible to evaluate on an academic budget. They include many different tasks from the the PD solving task we've discussed, the protein folding tasks from genomics, audio, and so on. And we also have evaluated different NOS methods at different budget constraints on these tasks and have some interesting results. And finally, we're also working on new search spaces. So far we've developed a search space that contains a lot of interesting operations. As I've discussed, it contains graph convolutions, it contains these FNO operations, many different kind of standard convolutions or transpose convolutions, and of course an infinite number of operations because it is a continuous space. On the other hand, it doesn't contain everything. As was mentioned, it doesn't contain things like max pooling or nonlinearities. It doesn't contain self-attention. So this is a plot of what like this transformer architecture, self-attention architecture actually is. And so of course it's not going to contain everything we might want because there are many different nonlinear operations that we might care about. But the goal, I think, is to see if similar ideas to XD can be applied to define new search spaces that are efficient to search over, but contain maybe some of these operations and of course many more. So different types of convolutions, say approximations to self-attention, which is a very important task since self-attention is quadratic. Can we similarly find kind of an elegant definition such as ours to encode these operations in a way that makes them searchable and also usable for new applications? And so that largely concludes my talk. I hope I've convinced you of the importance of studying diverse applications using neural architecture search, and hope you can also try out our method, which is available as software on GitHub. I'd like to thank my collaborators, of course, Nick Roberts, who co-led the work with me, Tree Dow, Liam Lee, Chris Ray, and Amit Talwalkar. And you can also see our paper, which will appear at the NeurIPS conference and machine learning this December. It is an archive. And of course, please feel free to email me with any questions.
Thank you. Thank
Thanks.
you so much. Yeah, thank you. Thank you, Misha, for the wonderful talk. It was wonderful. Let's have a Q&A sessions. You can either post your questions to the chat room, or you can unmute yourself and directly ask questions. Let me start with my question then, while you guys are preparing your questions. So the challenge of the PD solver is that as the problem can get pretty complex and becomes large very easily, and therefore the simulation data can be large, and the corresponding image can be very large, and therefore the neural net architecture, it has to include a lot of parameters and noise and edges, etc. So I guess the XD is slower actually than the CNN in terms of training. So I guess that has to be addressed further in order to be applied to truly large scale problem, I guess. Yes. If you can comment on that.
Yes, so that is definitely true. In order to apply this to truly large scale PD problems, you will need to address this problem. There is, I think, some hope in that our collaborators are working on, I think, more like better structured matrices than the K matrices that might be faster, more GPU friendly. There's also work on truncating the things we need to do, or the kind of truncating the outputs of, or the input to these K matrices in order to make the input smaller while not actually losing so much error. It's a bit difficult to get into, but basically there's a lot of padding involved and you end up with a lot of zeros in places in the internals once you try to actually multiply all these things. And kind of getting rid of these zeros would hopefully get you better results. I think there's also hope in the sense that, for example, FNO is actually a very efficient operation. Not XD, but FNO is actually quite efficient. It is more efficient, I think, than CNNs, at least in the applications we've tried. And there's hope, I think, in sort of using similar structures to what they're doing. So, for example, restricting ourselves to a search space that contains FNOs but does not contain convolutions. There are ways to do that I think might be faster than forcing ourselves to contain convolutions. So I think there are definitely directions for making this faster for that application specifically. And
Yep.
those directions will hopefully be useful to other applications that also require speed.
Yep, cannot wait until that's actually come true. My next question is some sort of clarification question. XD, you said cannot apply to the nonlinear operators, such as the some nonlinear activation functions. But that doesn't mean that you cannot use nonlinear activation
Yes.
function in your neural net. It's just you are not searching for those, activation function in your
Yes,
search
that's
space,
exactly
right? Yeah. Okay.
That's exactly true. Yes. Yeah, it's just you substitute in like a convolution is itself not a nonlinear operation. You substitute for the convolution, but then you maintain the nonlinearity after it, and that's how it works. So yes, all our networks I think contain ReLUs. Yes.
Great. Okay, is there any other question from audiences? You can. Okay, Kevin asked, how much more expensive is it on memory usage? I guess he's talking about the XD.
Yes. So memory can also be challenging. It can be up to 2x more expensive, 5x more expensive on memory as well. I think it basically aligns with the computational expense, and this is something also that we're working on. Yeah, I think specifically the idea of truncation, which is something that FNO uses to make it more efficient, is something that will hopefully also make this more efficient, and basically reduce the like large kind of entries of zeros we're passing around.
Right, sounds good. Thank you. The next question is from Charles. He asked if it's too expensive to apply XD on his full data, will it be worthwhile to apply XD on part of his data? Let's say he could only run XD on 100th or 1,000th of his full data. A partial application of XD too. Yeah.
So certainly there's a question of whether you can develop trade-offs between having more samples and having a more expensive network, right? So for example, the FNO approach, since it's more efficient, you might be able to run it on more data more quickly and get better results. On the other hand, to train XD, it takes a lot longer. And so you might not be able to train it on as much data, but it is a bit better. So you can develop kind of like a trade-off curve there of at some point, maybe if I have enough data, I've run my classical solver for long enough, then you should maybe use FNO. Or if you don't have a lot of data, then you can use XD. And that will be better. It does depend on your problem, and maybe there is a trade-off that can be found that is advantageous for our case.
Okay, great. All right. I have one more questions. You said, well, I'm just curious. You suggested to combine the, topology search type of NAS and your XD types of NAS. They can be combined. Maybe topology can be, optimized first and then apply the XD after that. Yep. How about optimizing both simultaneously, both search space? Do you think that is possible?
It's going to be a bit trickier, I think, to do that simultaneously, depending on exactly how you want to do it. But it might be tricky because the Dart search space and many other kind of classical topology search spaces are discrete. And so if you optimize them simultaneously, you're going to have to round after your training procedure. And that might ruin kind of any benefit you're getting from XD because you've kind of changed your network structure dramatically once you've rounded.
Got it. Okay. Yeah. So it's like you're solving like discrete continuous optimization simultaneously.
Yes. Yeah. And so that's the
Right.
difficulty there.
Okay. Sounds good. All right. Is there any other questions from audience? You can unmute yourself and ask question directly. Well, if not, let's thank our speaker today for the wonderful talk, Misha from Carnegie Mellon. I think we all have learned a lot, and we all agree that XT or NAS in general is very useful. So thank you so much, Misha, for the wonderful talk, and I hope that the future collaborations will happen, after this the DDPS seminar. So thank you. Let's thank Misha.
Yep. Thank you so much for having me. This was very great questions.
Great. All right, let's conclude the seminar today. Thank you so much, everyone, to joining us, and I think we will have another DDPS seminar next week. If not, then 2 weeks from today. Until then, stay healthy, everyone. Okay, bye, everyone.